Welcome to Thermodynamics and Equilibrium 4. So this is the final lecture on this topic. So in this lecture we will summarize the previous lecture where we were looking at the relationship between delta G and the equilibrium constant K. And we'll make it so that we can use Van 't Hoff equation and derive thermodynamic parameters from for the equilibrium process from two experiments that were carried out at two different temperatures. I'm also going to introduce to you the partition coefficient as an example of a physical equilibrium process. So if we do the two experiments, we can access all the thermodynamic parameters, as I've said, and we will use these three equations to do it. Now, I've introduced a number of equations to you throughout thermodynamic lectures, and I will soon put up a document onto Blackboard that will show you how I would expect you to be able to use equations in an assessment. I do not expect you to memorize these sorts of equations. If you need to use them, then they will be provided in any formal examination setting. So here are two experiments. Experiment 1, we've measured K1 at T1 at temperature 1, and experiment 2, we have measured K2 at temperature 2. So we can do this because we can calculate the equilibrium constant for measuring the concentrations of reactants and products at equilibrium. We can now easily calculate the change in Gibbs free energy, so delta G, and we can calculate this at both temperatures using this equation. So we can calculate delta G T1 using the experiment 1 data, or delta G T2 using experiment 2 data. We're not assuming that delta G is the same at different temperatures. We know that it will not be. We can work out the enthalpy, the change in enthalpy, from our Van 't Hoff equation. So here we have all of the values in this equation are known. We have the gas constant, which is known, and we have the equilibrium constants at the two temperatures of our measurements, which are all known. And so we can use this equation to work out the change in enthalpy. So we can work out delta H from this equation. The final thermodynamic parameter can now be calculated, and that is delta S, which can be determined from this equation and is now the only unknown term. And we can work it out using data at temperature 1 or data for delta G at temperature 2, and you should get the same value for delta S, whichever you use. As mentioned earlier, delta H and delta S are assumed to be temperature independent for these calculations. So just to go through that one more time, if you have a drug X that binds to a protein Y and this forms our complex Z, you would end up with an equilibrium of X plus Y, the drug binding with the protein to form the complex, but can also unbind and separate to go back to X and Y. So you would get an equilibrium reaction. Now the equilibrium constant for the forward direction of this reaction is K, and K will be equal to the concentration of the product over the concentration of the reactants. So it will be Z over X and Y. Now this means that if we do the experiment at two different concentrations, we will have two different values of K, and at two different temperatures, we will have two different values of K. And we can work out equilibrium constant, as I've just said, and all the thermodynamic parameters. So why do we care? Well, we will know under what conditions product is favoured. So in what conditions the complex is favoured by doing these calculations, because we will know whether it is entropically or enthalpically driven process. So whether it's entropic interactions such as hydrophobic interactions or enthalpic interactions, say largely electrostatic perhaps, that might be determining the binding of X and Y together to form the complex. And so by this knowledge we can create conditions that would favour the formation of the complex. So in summary, we can work out K, our equilibrium constant, from the concentrations of reactants and products. We can determine delta G from those two values at one temperature, and we can repeat that to determine delta G for the other temperature. We can use Van 't Hoff equation to obtain delta H, and then we can work out delta S. And then we can work out the dominant contribution of delta G for the reaction to determine if it is enthalpically or entropically driven. Remember, if delta H is negative and minus T delta S is less negative or is positive, then we would know that the process is enthalpically driven. Whereas if delta AS is positive, so that minus T delta S is very negative, and delta H is positive, so in other words the enthalpy is endothermic, we would know that we had a process that was entropically driven. In other words, the reason why the reaction occurs is because of a change in entropy, so an increase in disorder of the system rather than a change in enthalpy. And this helps us to understand that binding process, or that interaction that allows the reaction to occur. So the easiest thing to do when you're thinking through what I have just said in terms of how delta H and delta S change, it's using this equation, delta G equals delta H minus T delta S. And remembering that for the reaction to occur spontaneously, delta G needs to be negative. And we will know whether it's enthalpically or entropically driven based on whether it is the delta H component or the minus T delta S component that gives delta G its negative value. And that is the end of that topic. I'm going to finish this lecture by talking about a different type of equilibrium process now. We can use the concepts of equilibrium that we have learnt to consider equilibrium partitioning of a drug between two phases, an aqueous phase and an organic phase. Now this allows us to understand if the drug is more lipophilic, so lipid oil liking, in other words it would reside in the organic phase, or whether it is more hydrophilic, where it would reside or prefer to reside in the aqueous phase. And this is a concept we use to determine how well a drug might partition across a membrane and be absorbed into the bloodstream. In this diagram, our drug starts in the aqueous phase, and we will be able to see it move or partition into the organic phase until an equilibrium is reached. So you can see that molecules will gradually cross into the organic phase. These are two immiscible phases, so they don't mix until we get to a point of equilibrium where the same number of molecules are going from the aqueous phase to the organic phase than are going from the organic phase to the aqueous phase. And so at this point we have equilibrium. And you can see that our equilibrium point, there are more molecules now in the organic phase. So this molecule is fairly lipophilic. So it likes the organic phase more than the aqueous phase, but it is soluble in both phases. This process is a physical, as in it's not a chemical reaction, equilibrium. It's a physical equilibrium as we go to a point where we have partitioning at equilibrium of our molecules between the two phases. As we know for a reaction, the equilibrium constant is products over reactants. So for this equilibrium partitioning, the equilibrium constant, which is now known as the partition coefficient, is calculated as concentration of drug in the organic phase over concentration of drug in the aqueous phase at equilibrium. So it's the same structure of an equation that we would see for our equilibrium constant. So the partition coefficient is our physical equilibrium constant here, and it is the concentration in the organic phase over the concentration of drug in the aqueous phase. So in this example, we started with 12 X's, so 12 molecules in our aqueous phase, as you remember. And at equilibrium, there were 3 molecules, 3 X's in the aqueous phase and 9 X's in the organic phase. So that means our partition coefficient is 9/3, so it is 3. And this is, as you can see, a relatively large number. It is above 1, so it shows that the drug has a preference for the organic phase, for the lipid phase. We can use other thermodynamic equations that we used for equilibrium constant, for partition coefficient, and for this physical equilibrium as well. So using our equation that we have seen for chemical equilibria, we can calculate the change in Gibbs free energy for the process of the molecule partitioning into the organic phase for our drug X at the physical equilibrium, with P now being used in the equation instead of K. So we use the partition coefficient in the equation now instead of the equilibrium constant. Remember, P is an example of an equilibrium constant, but it is not a chemical equilibrium. It is a physical equilibrium. So finally, this table here looks at how delta G and the partition coefficient will change and the impact that has in terms of whether our molecule favours the organic phase or the aqueous phase. We can see that the organic phase is favoured when the partition coefficient is greater than 1. And then delta G for partitioning into the organic phase is negative. If our partition coefficient equals 1, the drug is equally happy in either phase. And if our partition coefficient is less than 1, then the aqueous phase is favoured. The position of the equilibrium is determined by delta G of the reaction, if you'd like to call it that, of going from the aqueous phase to the organic phase. So that partition process of going from the aqueous phase to the organic phase. And if that is overall negative, then we will have a system where the organic phase is favoured. So if X is nonpolar, it will tend not to interact favourably with the aqueous phase, and P will be greater than 1. And if X is polar, it'll tend to interact favourably with the aqueous phase, and so P will be less than 1. Now we will discuss log P later when considering solutions and drug absorption. So here I've been talking about the partition coefficient as P, but as you know, when we talk about drug absorption, or you may have heard this term before, then we tend to log that value and use log P as our term in consideration of drug absorption. So that is the end of our lectures and on thermodynamics. The summary of this lecture is that you have seen how we can use key thermodynamic equations to derive our thermodynamic terms, and then we use that to discuss enthalpic and entropic processes, and partitioning as an example of a physical equilibrium. What I want to do with these lectures now is for us to meet next week. So we will have a Blackboard Collaborate session, and I will go through key concepts that have come across in these lectures, and we'll study a few of the more difficult concepts in more detail together. We will also have a tutorial workshop, and you will go through some questions. You'll be given a worksheet based on these lectures to do for that tutorial workshop. And that is the thermodynamics content for next week. So this week, focus on going through the lectures, and next week we will use the lectures together to go through key concepts and to go through a worksheet.